times in our dealings with power series, we might want to take the derivative or we might want to integrate them. And in general, we can do this term by term. What do I mean by that? Well, that means that the derivative of f prime of x, is just going to be the derivative of each of these terms. So that's going to be the sum from n equals 1 to infinity. And let's see, the derivative of x to the n is n times x to the n minus 1. So I could write this as n times x to the n minus 1, all of that over n. And these n's will cancel out. So this is just going to be x to the n minus 1. So this is taking the derivative with respect to x. Similarly, we could integrate. And we could evaluate the integral of f of x dx. And this is going to be equal to some constant plus if we integrate this term by term. And so this is going to be equal to the sum from n equals 1 to infinity. And let's see, we increment the exponent, so x to the n plus 1, and then we divide by that. So times n plus 1 times this n right over here. So this is a common technique that you will see when dealing with power series. And we're going to go a little bit more into the details, because you can only do this for x values within the interval of convergence for the power series. And as we will see, the interval of convergence for these different series is slightly different. The intervals are very similar, but what happens at the endpoint is different. So I encourage you, pause this video and see if you can figure out the interval of convergence for each of these series. This is the integral of our original series, and this is the derivative of our original series. So let's start with our original series. Let's figure out the interval of convergence. And we could do that using the ratio test. So the ratio test, we would want to do the limit as n approaches infinity of a sub n plus 1, so that's going to be x to the n plus 1 over n plus 1 divided by a sub n, so that's x to the n over n. So we want to take the absolute value of that. That's going to be the limit as n approaches infinity. Let's see, this is, if you divide this and this by x to the n, that's going to be a 1. And this is just going to be an x. And then this n is going to end up top. So this is going to be xn over n plus 1. And this is equal to the limit as n approaches infinity of, let's see, if we divide the numerator and the denominators here by 1 over, if we divide both of the numerator and the denominator by n, we're going to get x over 1 plus 1 over n. And what is this going to be? Well, this term's going to go to 0. So this is just going to be equal to the absolute value of x. And the ratio test tells us that this series is convergent if this right over here is less than 1. It's divergent if this is greater than 1. And it's inconclusive if this equals 1. So we know, let's write that down. We know we are convergent for the absolute value of x less than 1 when this thing when it is less than 1. We know that we are divergent when this thing is greater than 1, when the absolute value of x is greater than 1. But what about when the absolute value of x is equal to 1? That's where the ratio test breaks down. We have to test that separately. So let's look at the scenario where x is equal to 1. When x equals to 1, this series is the sum from n equals 1 to infinity of 1 to the n over n. Well, that's just going to be 1 over n. This is the harmonic series, or the p series, where our p is 1. And we've seen in multiple videos that this diverges. So when x equals 1, we diverge. But what about when x equals negative 1? When x equals negative 1, this thing becomes the sum from n equals 1 to infinity of negative 1 to the n over n. And this is all often known as the alternating harmonic series. And this one, by the alternating series test, this one actually converges. And we've seen that in multiple videos. So it turns out the interval of convergence for our original thing right over here, our interval of convergence here is x can be So it could be x can be greater than or equal to -1, or I could say -1 is less than or equal to x, because if x is -1, we still converge, but then x has to be less than 1, because right at 1 we diverge, so we can't say less than or equal to. So this is the interval of convergence for our original function. What about the interval of convergence for this one right over here, when we take the derivative? Well, when we take the derivative, this is the same thing as x to the 0 plus x to the first plus x to the second, and we go on and on and on. Now you might recognize this. This is a geometric series with common ratio of x. Geometric series where our common ratio, often denoted by r, is equal to x. And we know that a geometric series converges only in the situation where our common ratio, where the absolute value of our common ratio, so converges only in the situation where the absolute value of our common ratio is less than 1. So in this situation, when we took the derivative for f prime of x, our interval of convergence is almost the same. So here our interval of convergence is going to be x has to be between -1 and 1. But it can't be equal to -1. If at -1 we would actually diverge, and at 1 we would diverge. So notice these are almost the same. If we view these as series centered at 0, the radius of convergence is the same. We can go 1 above, 1 below, 1 above, 1 below. And that's in general true as we take derivatives and integrals. But the endpoints of our interval of convergence can be different. And to continue to see this, I encourage you to use the ratio test to figure out what is the use a ratio test plus using the boundary conditions, figure out what the interval of convergence is for the antiderivative, for the integral here. And what you will see is the radius of convergence is the same. We can go 1 above 0 and 1 below 0. We have to be in that interval. But as you will see, this one converges for x equals -1 or x equals 1. I'll just cut to the chase here. So interval of, let me write that in yellow. The interval of convergence for this top one converges for -1 is less than x is less than or equal to 1. So notice they all have the same radius of convergence, but the interval of convergence, it differs at the endpoint. And if you want to prove this one for yourself, I encourage you to use a very similar technique that we used for our original function. Use the ratio test. You're going to come to this conclusion right over here, and then test the cases when x is equal to 1 and x is equal to -1. And you will see when x is equal to -1, you have an alternating p-series, so that's going to converge. And then when x equals 1, you're going to have a p-series where the denominator has a degree larger than 1, or something similar to a p-series. And you can establish that it will also converge in that scenario as well.